Good day, Professor, and all students watching this presentation. This is our final team project for Statistics for Predictive Analytics in spring 2019. The topic we chose is House Prices Regression. Our team consists of myself, Jason Canonigo, Suganthi Babu, Luis Cardenas, and Sanjin Hadzik. The agenda or overview of this project comprises of the problem statement, data understanding, data processing, model and validation, and the conclusion. For the problem statement, the objective is to predict the price of housing based on the given information from the predictors, which we mention in the upcoming slides. The value and emphasis is to understand the purpose of this analysis for both professionals and the public whom are interested in the prices of houses. For example, respectively, real estate agents and bankers, and home buyers and home sellers. There are many key performance indicators, and in this study, we used RStudio to create predictive models to analyze the data and identify the most influence attributes which would impact the sale price. We have chosen 5 different models, and the results will be discussed in detail later in this presentation. Our data came from Kaggle, which the link is located in the reference slide. This is where we examine the property data in Ames, Iowa, including the quality. The training data set consisted of 1,460 observation points, a total of 79 numerical and categorical predictors or attributes, and the sales price being the response variable. Some of the main examples were the construction date, when the house was built or the age of the house, location, where the house is placed and its surroundings, lot size or plot that is owned or meant to be owned by some owner, number of bedrooms, the amount of rooms that is meant to be slept in, and square footage, the measurement of the total area within the house. In this slide, on the left, we have a distribution of sale price histogram. This essentially shows that most houses are bought between $150,000 to $250,000, and on the other hand, the least and most expensive houses are not as frequently bought. On the right, we have a collinearity chart, which identifies 2 or more variables that are comparatively similar to each other. After finding the highly correlated predictors, we remove them from the data. And I would like to bring your attention to the dots on the right of the chart. The strong blue and orange values that are circled in the red ellipse are correlated with the sale price, and we use these variables in our model. This slide shows the histograms of all the distributions of numerical predictors and how they summarize and display the process data. The key takeaway is to notice how the variables are dependent to each other. Additionally, what information is and what is not necessary. For example, you will notice the ID on the top left corner is a uniform distribution, which is not necessary for our data analysis. Here are more histograms further showing us the importance of the frequency of occurrences in the continuous data sets. In this slide, the missing value analysis graph clearly shows us what data fields we should exclude. More specifically, the variables we identified with the most not applicable or NA values from this graph are not going to contribute to the model, and hence it should be excluded during the data processing. So after the data was cleaned up, the obvious variables were number of miscellaneous features, number from fences, number from pool quantity, number from fireplace quality, and the number from alley. And again, these were omitted from the analysis. These are the 12 steps to understand our approach we took to achieve our data processing. Step 1, the raw data was received from Kaggle, and we found the training data sets, predictors, and numerical response. Step 2, we eliminated any data that had a significant amount of NAs. Step 3, the duplicate data was taken out. Step 4, remove collinearity, and as it was discussed in slide 6. Step 5, select the strong predictors, which will be discussed in the next slide. Step 6, the similar types of attributes were totaled, and then the sum was used for the data. Step 7, transformed any attributes that required meaningful data. Step 8, the data is cleaned up of all the unimportant attributes so the data is not compromised. Step 9, for all other NAs not relevant in Step 2, the average of the numerical data set was put in its place. Step 10, converted the sale price to thousands for a more accurate graph depiction. Step 11, identify outliers in the dataset that might cause problems or errors in the analysis and remove them. And finally, step 12, the linear dependencies were determined and eliminated. Here we list the numeric and categorical variables, that is the future names. And I will go over some of the ones that are least obvious, like the fourth one down, which is masonry veneer area, that is the material of the exterior. Below that is the garage living area. And the third one from the bottom is total square footage. After the data processing, the number of observations was narrowed down to 91 and the attributes to 18 predictors. The model and validation slides will demonstrate the models we use to build our project. They are forward stepwise selection, backward stepwise selection, ridge regression, the lasso, and principal components regression. The forward stepwise selection, mentioned in Chapter 6.1.2, is a proficient option for best subset selections. This process starts the model without predictors and adds them one by one until they are all in the model. The model displayed in this slide compares the residuals versus the fitted variables. Additionally, we used tenfold cross-validation, and both train and test gave the same positive and negative coefficients for R-squared, adjusted R-squared, and root mean square error, or RMSE. As a result, you will notice R-squared is 86.7%, while the RMSE is 1.729. For this and for further slides, please note that the negative and positive coefficients. That is, when that independent variable increases by 1, the dependent variable is likely to increase if the coefficient is positive, or is likely to decrease when it is negative. The backward stepwise selection, also located in the same section, is like forward stepwise selection, except it begins with the model that contains all the predictors, and then removes the least useful predictors one at a time. For example, in this case, central error was excluded from the coefficient. We also use tenfold cross-validation for this model. And in this graph, you can view the relationship between residuals and leverage. Based from the results, we can see that the R-squared is 86.3% and RMSE is 1.75. Ridge regression, studied in 6.2.1, is a counteractive measure taken to improve the multicollinearity amongst the regression variables in a model. Often predictive variables used in a regression are sometimes highly correlated. The method used here adds a small bias feature to the variables in order to relieve this problem. We used a function which by default performs tenfold cross-validation unless we specify a value to the parameter. The graph shows the correlation to RMSE and lambda, that is a tuning parameter, and the outcome of ridge regression indicates that R-squared is 86.9% and RMSE is 1.799. The lasso, which means least absolute selection and shrinkage operator, was discussed in Chapter 6.2.2. So the disadvantage to ridge regression is that it includes all the predictors in the final model. The lasso is an alternative to ridge regression that overcomes this disadvantage. It produces a simpler and more interpretable model that involves only a subset of predictors. Like ridge regression, lasso shrinks the coefficients closely to 0, but lasso brings some of them exactly to 0. Furthermore, this model performs a tenfold cross-validation as well. With that said, you can now see the difference between the graphs from the previous slide and the graph displayed here. Now lasso gets the following new outcomes. R-squared is 87% and RMSE is 1.786. Principal components regression approach, as we learned in 6.3.1, encompasses constructing the first principal components, that is the regressors and independent variables, and then using these components as the predictors in a linear regression model. By using the CV as a validation in the PCR function, we compute a tenfold cross-validation error for each possible value of principal components. In doing so, we will see a graph representing the correlation and that more components result in less MSEP. Additionally, R-squared is 84.8% and RMSE is 1.589. This slide represents the results from all the models, which all of them use the tenfold cross-validation. Please take a moment to recognize lasso highlighted in green and PCR highlighted in orange. Based on the comparison, The lasso is the best model for the house pricing dataset used in this project. Moreover, we concluded lasso is the best model because R squared and adjusted R squared are higher than the other models. Although PCR has the lowest RMSE, it also has the lowest R squared and adjusted R squared, which is why it was not the preferred model. Many insignificant variables were taken out of the data, but having a large volume of data was an important start to determine what variables were best to establish the house prices. Overall, the price of the house can be easily formulated based on the most common predictors. Based on the models that we used for this project, we conclude that many different factors influence the price of housing, as displayed in the chart. The main factors were 1. How the type of neighborhood can impact the sale price negatively or positively. 2. The overall quality of the house influenced all 5 models. And 3. The fair to average kitchen quality and duplex and townhouses negatively impacted the house prices. These are the references we used for the project. Ladies and gentlemen, that concludes our presentation. For any questions or feedback, you may reach us through our email address provided. And on behalf of Team 6, thank you for listening, congrats on making it through the semester, and have a wonderful day.